You know, if you really tune in, you can almost hear two different hums powering our world. One is this ancient biological hum. It's the sound of mitochondria, the tiny power plants inside every one of your cells. The other is brand new. It's digital. It's the hum of GPUs, the engines that are driving this whole AI revolution. Now, on the surface, you've got life and you've got silicon. What could they possibly have in common?
So that's the big puzzle we're going to tackle. Is this whole comparison just a neat little analogy, a fun party trick for thinking about AI? Or is it pointed to something way, way deeper, a fundamental blueprint for how complex systems actually work? Well, let's dive in and find out.
So here are our two worlds, side by side. On the left, you've got the hum of life, totally driven by the chemistry of carbon. And on the right, you have the hum of inference, driven by the physics of silicon. I mean, they seem like they're from completely different universes. But today, we are going to build a bridge right between them.
To build that bridge, we've got to start on one side of the canyon, and we're going to start with biology. We need to talk about the universal currency that is literally powering you right now, letting you think, letting you breathe, everything.
I want you to meet ATP, adenosine triphosphate. Now, the key thing to get here is that ATP isn't just energy in some vague sense. No, it's a standardized packet of energy. Think of it like a tiny, perfectly formed, rechargeable battery. It's less like a big chunk of coal and more like a universal coin that every single part of your cellular economy accepts as payment.
So how does the cell actually make these little energy coins? Well, it starts with raw fuel, right? Like the sugar from the food you eat. Then it puts that fuel through these incredible chemical assembly lines, breaking it down and refining it into those perfect standardized ATP packets. And only then, once it's in that universal format, can that energy be sent out to do all the work, from making a muscle contract to firing a neuron.
And this quote just nails the point. A cell can't just shove a sugar molecule out of muscle and say, hey, move. It wouldn't work. It's not the right format. It needs a medium of exchange that everything understands. ATP is that medium. It's the dollar bill that every part of the cell has agreed to accept.
Okay, so hang on to that idea tight. Raw fuel is converted into a standardized universal currency. Got it? Good. Because now we're going to walk across that bridge into the world of AI, and you're about to see a pattern that is shockingly familiar.
And there it is. The token. Just read that definition. Does it sound familiar? A token isn't a whole idea or a complete sentence. It's a packet. It's a standardized, chopped up piece of the whole. It's the basic unit of information that a large language model actually operates on.
And look at this. The workflow is practically a mirror image. The AI starts with its raw fuel, our messy, complicated human language. It runs it through a standardization process, chopping it into tokens, and then converting each one into a mathematical vector, basically a point on a giant map of meaning. And only then can it use those standardized tokens to do its actual work. This is just such a perfect way to phrase it. Just like ATP is the unit for biological metabolism, the token is the unit for an AI's linguistic metabolism. It's the fundamental piece that gets processed, transformed, and spent to create an answer. Okay, so we've looked at the two systems on their own. Now it's time for the big reveal. This is the moment where this whole thing stops feeling like a fun metaphor and starts looking like an engineering blueprint. And here we go, the deep structural parallel. Just look at how cleanly this all maps. The raw fuel, glucose for life, raw text for an AI. The conversion process, glycolysis for us, tokenization for them. The universal currency, ATP, becomes the token. The way you spend that currency, ATP hydrolysis, becomes a forward pass computation. And the power plant that makes it all happen, the mitochondrion, it becomes the GPU. I mean, come on, this isn't a loose comparison anymore. It is a direct, one-to-one architectural alignment. It's actually kind of uncanny. But believe it or not, it gets even deeper. See, it's not just that the components look the same, the processes are running on the same playbook too. These aren't coins that you just spend once and then they're gone. They exist inside this beautiful, dynamic, repeating cycle.
Just look at this. In biology, an ATP molecule is spent, it turns into ADP, and then it gets recharged right back into ATP so it can be used again. It's a constant loop. Now, look at the AI. A token is processed. That helps create the context to predict the next token, which then gets added to the chain, becoming the fuel for the next step. Each output becomes the next input. It's a beautiful, self-perpetuating cascade in both systems.
And that brings us to the power plants themselves. Your mitochondria and a Google data center are both what scientists call gradient transducers. Now that's a fancy term, but the idea is actually pretty simple. They both take a big, messy, powerful flow of energy, a chemical gradient for mitochondria, an electrical one for data centers, and they convert it into a smooth, steady stream of these small, useful packets. The source material calls data centers Shannon mitochondria, and you can see why. They're performing the exact same structural function.
Okay, so we've laid out the what. The parallel is deep, it's real, it's structural. But that just brings up the biggest question of all, doesn't it? Why? Is this just some kind of wild cosmic coincidence? Or is there something more fundamental happening here?
Well, the answer seems to be that both systems independently discovered the best solution to the same problem. Think about it. If you need to coordinate billions or trillions of different jobs, you need a currency that's broken up into little pieces, quantized. It has to be easy to move around, portable. Every part of the system has to accept it, universally compatible. And it's got to be recyclable so you don't run out. This isn't an accident. It's convergent evolution. It's just smart design.
And this really brings us to the core insight of this whole thing. This was never just about biology and AI. It's about a universal principle of complex systems. As the quote says, any system that gets complicated enough to create order out of the universe's natural chaos, it eventually figures out it needs a currency to do business. Life, facing the problem of coordinating trillions of cells, invented ATP. AI, facing the problem of coordinating billions of parameters, invented the token.
So let's end with this one final thought to really chew on. If today's AI models, with their token-based metabolism, are kind of like the first single-celled organisms, what comes next? Because biology didn't stop there, right? It evolved into multicellular life with specialized organs and brains and complex ecosystems. So, as we see AI starting to use tools and access memories and talk to each other, are we actually witnessing the dawn of a new kind of multicellular intelligence being born from silicon? And what in the world is that going to look like?